So is my screen visible? Okay. So welcome to this course. Now we are in the eighth week of this course, and so the end date is 14th of October, and your exam date is I think on 29th. So, if you have any questions, please ask your questions in the SWAM portal in this Ask a Question tab, and the professor or the TA when they will as and when they will see they will respond, and also let the others know so that the others who might also have the doubt can clear will get their answers. So, will come. Sorry. So should be. So. Uh, we will today discuss. We are in. This is the ninth session, and we today we will be discussing about the seventh assignment, uh, which was so have you have given your seventh assignment, right? Yeah. So you have given it. So maybe there is some error here. So it was will be 2 to 3 days before, I think. So the questions on the seventh assignment were basically about the structure factor things and all. So in addition to what the professor has taught, I will just briefly touch upon some topics which might help you to get a better understanding of those ideas, and particularly in the context of solving the assignment questions. So at first let us understand that what is this structure factor. So structure factor is nothing but the physical significance of structure factor is that how material scatters the incident radiation. So when we are shining x-rays, then the x-ray is the incident radiation, and how any material will scatter that incident radiation is the physical significance of structure factor. And then mathematically we go into many formulas and equations to find out the structure factor, so that we can find out the structure of the of our system, of our material. So here what happens is we will consider our material as good single crystals. Then if our material is a single crystal, then it will if we follow the Bragg's law, the Bragg's hypothesis, then the crystal is made up of many kinds of planes, HKL planes, and every HKL plane will have a structure factor. Why? Because in every HKL plane there will be some atom in that plane, so there will be some electron density in that plane, and when there is X-ray falling on that plane, then the electron densities or the atoms will scatter the X-rays, and we will get the structure factor of that plane. So the structure factor basically comes from the scattering centers or the atoms which are present in the different HKL planes. So this is the formula of the structure. Yeah, you want to say something? Yes, yes. This is all one scattering this X-ray, na. So these are all elastic scattering, okay. But sometimes there can be inelastic also. So that is something called as the anomalous scattering or anomalous dispersion. Okay, so but mostly it is actually depends on the crystal systems, you know. So mostly when we take if the crystals are centrosymmetric, then there is normal elastic scattering. But if the system is non-centrosymmetric, then sometimes it can cause this anomalous dispersion or anomalous scattering. But usually we take it as elastic. Okay. So, the structure factor for a system with many atoms, with each where each atom. If there is a plane with many atoms, then different. Suppose in the same plane there can be a metal atom and a carbon atom. So obviously the metal atom will scatter more than the carbon atom. So even if we consider one plane, in that one plane the different scatterers or the different atoms will scatter to different extents, and that is the property of that atom, which is called as the atomic form factor. And the total scattering factor of a plane is simply the sum of all the scattering factors of all the atoms in that plane. So that is the simple explanation. So if the structure factor of this plane, of this HKL plane, is capital F, then it is the summation of over all the atoms 1 to n. If J is like, if there are suppose two atoms, then J will be 1 and 2. Then F1 is the corresponding atomic form factor for the atom 1, and F2 will be for the atom 2. And then this is one e to the power exponential term with e to the power 2 pi I, and then these are the what? These are the crystallographic coordinates of that scatterer of that atom. So what is happening is this atomic form factor is nothing but the electron density of the atom. Okay, so since the atomic form factor is nothing but the electron density of the atom, so sorry, so what we can do is we can write the expression for the structure factor in continuous form also. So here if we take this as the structure factor, then this is the integration over this electron density. So if we have one atom at position xyz with electron density rho, right, and the small volume it occupies is suppose dV, then if we integrate all the atoms we will get the structure factor. So this is what the equation simply is. Now if we think, now as if we assume that this thing, the left hand side, whatever is the value that can be measured, then if we can get this, right? So these are related. So if this we can somehow measure, then the electron densities can, how it can be obtained? It can be obtained through the Fourier transform of this structure factor. So here what we are doing is we will now make this as the subject. So this will come over here and this will go to the right hand side, and then we will get a formula like this, okay, where this upon integrating we will get the capital V, which is the volume of the unit cell, and then we will so here in this final equation we have the xyz, we have the structure factor which we can measure, and then we can find out the electron density, then we can find out what atom it is, because each atom will have it, its characteristic electron density, right? So so then to find out the that what the crystal is made up of, to find out the atoms we have to find out the electron densities of all the atoms. Now for that we will have to measure yeah, yeah, you can just like you don't have to raise your hand, you can just ask. Yeah. Yeah, so when we talk about isotopes, so suppose if we have carbon, right? So for carbon, what we have this, huh? Yeah, yeah, we have C12 and C13, right? So what is this 12 and 13? It is the atomic number. So atomic number means what? Atomic number is the number of protons. So, huh? Yeah. So see, every atom has three things. One proton, mane, three kinds of things: proton, electron, and neutron. So if we take 12 C12, it means it has 12 protons and it has 12 electrons. If we take C13, then no, I'm sorry, wait, sorry. C12 is the mass number, not the atomic number. That is what I'm saying. What are the atomic numbers? Atomic number is Z. Not laser, pen. So C12 we write on the top, na? And then C13. This 12 and 13 is the mass number. Okay, this is M. But if the atom is the same, then the Z is the same. Z is like 1 for hydrogen, and like this it is 6 for carbon. Hydrogen, helium, lithium, beryllium, boron, carbon. So here also it is 6, here also it is 6. That difference, so the number of protons is 6, here number of protons is 6. If number of protons is 6, number of electrons also has to be 6 because it has to be neutral. Electrons is equal to 6. Only difference in isotopes is in the number of neutrons, that is M minus Z. This is 6 here, and here the N is 13 minus 6, that is the 7. So it is same, the atomic number is the same. Hence if you take isotopes, it will have difference in NMR, not in single crystal. It will have the same form factor. Okay. So here, where were we? Huh. Yeah. So here, so we have this electron density. For this, we need to measure the structure factor. Now, this structure factor is a vector, and this structure factor vector can, if something is a vector, then it can be written as in terms of its amplitude and a phase. So every structure factor will have a phase. What is the phase? Phase is related to the origin. So what is the difference from the origin? That is the phase. So this is this FH scale, this is the magnitude, and this is the phase part. Okay. Now here you can see, so this phi h scale is the phase associated with the point in reciprocal space associated with the coordinates h scale. Okay. So this means that for to know this electron density, it can be split into these terms. Here we are simply splitting this FH scale, means this vector H scale, into the magnitude and the phase part. So now the structure factor, that is the capital FH scale, has the units of the electrons and the density. So this is, if something is electron density, then it will have the units of number of electrons per unit volume. So electrons divided by volume, which is my angstrom cube. Okay, so the density will have the units of electrons per angstrom cube, and the summation is over, will obviously be over all H scale values. And so this is not important, so the summation has to be carried out on as fine a grade of x, y, and z points as possible to obtain a smooth electron density distribution in the unit cell, and wherever the electron density is concentrated, it means there are some atoms there. Now so we will come to the questions now. So later we will understand this part, that what is the problem with single crystal data collection. The problem is that we lose the phase information when collecting all the diffraction spots in 3 dimension using the detector. We lose this phase information, we get only the amplitude, and that is why we then resort to some other methods to in order to completely understand the structure of the crystal. So we will read that later on. So now we will come to the assignment questions. So the first question was that the structure factor depends on the locations of the scattering centers. So this obviously has to be true, because the structure factor is simply the amount of scattering which is happening from the plane, from some H scale, suppose 111 plane. It will obviously depend on the atoms which are the scattering centers on that plane. Then this FHKL and rho XYZ. So this is the structure factor and this is the electron density. So these are related by a Fourier transform. So this will also be true. So this will also have to be true, right? Because we have like this is what we learned here. So these are also related by a Fourier transform and this is also related by a Fourier transform. So this will also be true. And then so we come to this third question. So this was interesting question, that if we have a centrosymmetric crystal, so this was true and false, and the statement was that in a centrosymmetric crystal the structure factor HKL must contain an imaginary part. So how to proceed with that? So what is a centrosymmetric crystal? So centrosymmetric crystal basically means that we have an inversion center. If we have an inversion center, then any atom which is at a location say XYZ, then we will get a corresponding atom at the location minus x, minus y, minus z. So these 2 points are equivalent points, right? So here we can consider any atom with form factor F at the position XYZ. So here actually I have solved it because it is very difficult to do by pen on the laptop screen. So I will like go through one by one. So we will first consider an atom at this position XYZ with an atomic form factor F. So this was given here already. So to consider any atom with form factor F at the position X, Y and Z. So if we do that, then if we consider an atom at this position XYZ with atomic form factor F, then because it is a centrosymmetric crystal, then there has to be an identical atom at the coordinates of minus x, minus y, minus z. So this is just the basic thing. If we put this thing na, so this XYZ is equivalent to x bar, y bar, z bar, or minus x, minus y, minus z, then we will just like this we will get the answer. So this actually very easy. So this is the structure factor equation, that it is summation over these atoms at the 2 positions. So now what we will do, we will split this. We will consider here 2 atoms, the equivalent atoms. So one will have the coordinates of x, y, z, and then another one. So here you can see. So if we split this into 2, so here Fn means the atomic form factors of the different atoms, but because it is centrosymmetry, so the atom at position XYZ is identical to the atom at position x bar, y bar, z bar. Hence this F and this F will be same. It is like F1 is equal to F2. So these 2 F will be the same. So for the first part we will write the same thing, e to the power 2 pi I hx plus ky plus lz, and then for the other identical atom we will write the F E, then e to the power 2 pi I, then we will put the coordinates of minus x, minus y and minus z. So if we now take the negative out from here, so it will this part will remain the same, and this will be e to the power minus 2 pi I hx plus ky plus lz. Okay, now what we will do is we will take this as some constant, not constant, we will take this as some phi. Why? So that we can use this formula. So this is a very common formula, so we have used it a lot in our like previous when we were studying, right, that e to the power I phi is equal to cos phi plus I sin phi. So what we will do, we will take 2 pi and this part as phi, then this will be e to the power I phi and this part will be e to the power minus I phi. So this we will then spread into this cos phi plus I sin phi, and then this part will be cos of minus phi plus I sin of minus phi. So here what will happen? So we know that cos of some negative angle is equal to the means cosine of some negative angle is equal to the cosine of that cos of minus theta. So we know that cos of minus theta is actually equal to cos theta, but sine of minus theta is equal to minus sine theta. So we will apply this formula here. So here this will be then the cos phi term, and this will also be the cos phi term, but here this will be minus I sin phi, this will be plus I sin phi. So this term and this term will cancel out. So this I, the complex parts or the imaginary parts are cancelling each other, and what we end up is 2 cos phi. So the question was that if the crystal is centrosymmetric, then the structure factor must contain the imaginary part. But what we are seeing here, that the imaginary part is cancelling each other here. Hence, that is why, so this the answer here will be false. Okay. So this will be false, and sorry. Yes. Um, yeah. Why? Why? No, this is those two what you are talking about. So these are not related. So if something doesn't have the imaginary part in the structure factor, but it still has a structure factor, right? Uh, no. See, these are two actually very much different things. So, any crystal, when we are taking under the this diffraction, X-ray diffraction, so every crystal will have some these planes, right? Every crystal has to have some HKL planes, so there will be some distance between the planes, right? The D. And when they will diffract, and when you collect the spots, then each spot uh, will represent one, each spot is collected in the reciprocal space only. So there is this directly we go to the reciprocal space when we collect the spots, because yeah, that part is not related to here, because we in the reciprocal space we get, if we get 300 diffraction spots, then each diffraction spot will have there are 300 structure factors, and inside the structure factor we can have imaginary part or not, that is different from there. Yeah, so every crystal will have D, the interplane distances, and also the D star rules. The fourth question was that the value of Rn progressively lowers as we keep on refining the data, as we better define the data during structure refinement. So, for data collection, we use some terms. The first one is the R int. The second one is the what we commonly call as the R factor, R1. Then we have the WR2. So these three factors are what commonly used when we talk about the data the structure, solution, and refinement, and how better is the refinement done and all. So what are these terms actually? Uh, so till now we have talked about this structure factors, right? So what we do, what usually happens is, suppose we want to collect the data of say manganese matlab organometallic system. We have suppose a manganese center. We took suppose the manganese nitrate salt, and then we took some organic ligand. We can take like ethylene diamine or something. Okay, so that is quite big. And then we can take manganese nitrate, and then when we get the crystals, so there will be many atoms, yeah, many number of atoms in that crystal. So out of so suppose we have taken this ethylene diamine, and suppose we have so manganese is octahedral, right? So we have to fulfill six coordinations. So ethylene diamine so there is this uh, 4n which can complex, and then the other two can be fulfilled by suppose salicylaldehyde, the CHO, the carbonyl of the salicylaldehyde. And then suppose that salicylaldehyde had some substituent like chlorine or bromine. So then in the structure we have heavy elements like bromine, manganese, and then we have comparatively lighter elements like carbon, nitrogen, oxygen, because nitrate will be has to be there to balance the charge and all. So comparatively lighter elements like carbon, nitrogen, oxygen, and then there will be lots of hydrogens also, which are like very light elements. So suppose we have this kind of a 30 atom structure, so there will be some heavy atoms initially. So what happens is, initially when we take the data, we get the structure factors without the phases, only the magnitude. So initially the phases of those are guessed by some programming method. So we learn about I think it is in your next week, Patterson method and all, I think so. So initially what happens is, initially the phases are guessed somehow. So what if we get some HKLs, we can get like 1000001s for some HKL values. So we guess the values of the what that what we guess that what will be the values of the phases, and then we get a structure factor which is called as the observed structure factor F0. So this F0 also we will get for like all the HKLs. So this can be written also as FHKL for a particular HKL plane. What is the observed structure factor F0? So you can also write it like this. Okay, so FHL. So initially the phases are guessed. So this is my observed structure factor. Then what we will do for the 30 atom structure, suppose we have like 20 atoms for which we can get the initial we can guess the initial phases and get the electron densities. Then if we after this Fourier transform, we will get the electron densities. We will be able to say that the 20 out of the 30 atom structure, 20 atoms are occupying this position. This is called as the partial structure, which we get after we do the solve part. Now this 20 atom structure which we got, that is the partial structure, and this is used as a structural model to determine the complete structure. Okay, so if the structure is about 30 atom structure and we know the position of about 20 atoms from the initial structure solution, what we do is we take those 20 atom coordinates and the 20 coordinates, and the corresponding electron densities are then known, because now we know that what atom is at what location. So from this row value we then do a inverse Fourier transform to get the new values of HKL, which we call as the calculated structure factor from the structural model. So at first we do the Fourier transform, and then we do the inverse Fourier transform. Then where we were actually talking about this RINT, right? So this is one example which I took from the internet. So suppose we have at first taken we have collected to 20,975 reflections. So this is like a complete data. Okay, so you can see we have suppose measured 20,975 reflections or spots, diffraction spots. Out of them, so only 200, 800, 2,847 are the unique reflections. Okay, what do you mean by unique reflections? Unique reflection means the number of independent reflections measured which are not repeated and not related by symmetry. Usually when we take a data, when we collect the spots, there is something called as redundancy. We take the same spot many times. That is a redundancy. Why we take? Because we do not have the phases, we take more data to calculate and guess. The more number of data we have, it is easier for us to guess the correct answer. That is why this redundancy is there. So if we remove the redundancy, what we have are the unique reflections. So you can see out of this 20,000, there are 2,000 something are the unique reflections, which are the number of independent reflections measured. They are the ones which is used for this initial structure solution, right? And here, from here we get, so these reflections, we have these unique reflections, and this gives me my R int. So this R int is, you can see, so this is the difference between the mean of the observed, means for every H scale, what is the mean. So if we have, like, we can have many H scale systems, right? Like 1 0 0 0 0 1 1 0 1, like this many we will have. Then for every H scale we will get one F01, F02, like this many F0s we will get. Then what will that this F0 squared mean? If I take, I will get some value. Then for every reflection, I will subtract this F0 square minus F0 square mean, and I will take the summation of that and divided by, so this is kind of normalizing thing, and this will give me my R int, right? So there can be many factors which cause higher R int value, so that is something different. But what I'm trying to say is, so in this R int we only have the observed structure factors, we do not have anything which is varying here. Hence R int does not change when we are refining the data. It is something which is obtained during the data collection, during the data reduction, and we cannot change it by better refining the data. So this is all, sorry, this is all about this R int. So R int, so this is actually the value of R1, which R1, which progressively lowers as we better refine the data during structure refinement. Because R1 actually represents the residual electron density, or the difference between the observed and the calculated model. So the lesser the difference, the better we are solving the data. Hence R1 will decrease as we better and better define the data, but R int is not affected by that. Hence this answer will be false here. So we will then move to the next question. That yeah, WR2 is also a factor. So you can see this. So this is my WR2, which is called as the actually this R factor, or this R1 came later. As you can see, R1 is simply the difference between the observed and the calculated structure factors. This is very simple, right? You can see this actually came because of the statistical reasons. But when we are solving the data, what we do is we take the calculated structure factors, take the difference of them, and we keep on optimizing it, right, every time. And with the statistical model, and our experimental model, and the difference there is called as the WR2. The formulas of WR2 and R1 are different. So you can see this is the formula of WR2, this is the formula of R1. So these are two different things. we see both, but usually we give more importance to R1 because when we solve the data, R WR2 is always like 2.5 times something of R1. So if it is easier to say that R1 is less than 10% means it is a good data rather than saying that WR2 is less than 25% means it is a good data. So it is a matter of convention. So we were here, right? So, so this was the next question that which among the following is not true? That so we can take we can see the question the statements one by one. So the first statement was that atomic form factor is a reflection of the electron density, which is obviously true. Then the next one is that the rho xyz, which is the electron density, can be obtained through the Fourier transform of the structure factor HKL. So this is also again true. Then the third statement was that the vector HKL can be written in terms of its amplitude and phase. So this is also again true. And then the last one is that the structure factor expression can be obtained without the atomic form factor, which is obviously not true because in this expression for the structure factor, so in the equation for the structure factor FHKL, in the beginning only we have the summation over n Fn, right? Where A is the atomic form factor. It is like if we have a HKL plane like this, we have some electron density here, some electron density here, small electron density here. So this might be a small atom like a hydrogen, suppose. This can be a very large atom. This can be a small atom. So this is 1, this is 2, this is 3. So this will be summation of, so this will be like F1 plus F2 plus F3, like this. So in order to get the expression for the structure factor, so we cannot do without the atomic form factor, right? So this one is the correct option. So then we go to the next question. So this is like, we come to systematic absences. So the question was that systematic absence for eye-centered cubic lattice occurs for HKL planes under which condition? So for that we have to go to the special form of structure factor. So till now we are learning about structure factors, and now what we will see is that this structure factor can be written in terms of this special form of structure factor, which is the sum over all the equivalent points. So this is actually nothing very new. We have been doing this before also. So for this special structure from the special structure factor equations, I'm sure you have gone through this video by the professor. So I am not going into the derivation of how we are deriving the EHKL from the FHKL. So I'm not going into that. So this is simply that what to do for body centered lattice. This was also, I think, one of the assignments given by the professor during his teaching. So if we have a body centered lattice, so the equivalent points are, so this is very simple, the equivalent points are x, y, z, and x plus half, y plus half, z plus half. Now again it is the same thing, we have to sum over all the equivalent points, right? So this one mistake here. This is a special, this is the special structure factor equation. This will not have the atomic form factor because atomic form factor is there in the structure factor. This is, which is capital F, FHKL, but this is EHKL. This will not have the F term here. So it's okay, I have corrected it. So here we will put the two equivalent atoms at we will put the coordinates the coordinates for the two equivalent atoms. So at first we will put x, y, z as x, y, z. Then we will put this as x plus half. So it is like this. You can just follow. So this is x plus half, y plus half, z plus half. Now you can like just do it in your copy. If you split this, so this will be what? This will be hx plus h by 2. This will be ky plus k by 2. This one will be what? This one will be lz plus l by 2. So this hx plus ky plus lz term you can take out common, because this hx plus ky plus lz term is here also. So from this term, the hx ky lz part you can take out, and then you can take common from the two terms, this part. Then what you are left with is 1, which means this part, and in this part you are left with 2 pi I, then h by 2, k by 2, l by 2. Then again these 2 you can take out common. If you take it out, you will cancel these 2's with these 2, right? It will cancel. Then what you are left with is e to the power pi I h plus k plus l. So in order to so the general here generally, so for this body eye centered lattice, right? We are talking about body centered lattice. For the eye centered lattice, this this condition, this h plus k plus l, what we are getting, this will have some condition for systematic absences. So let us see what are the conditions. So it can actually take only two possibilities, right? So there are, so for this h plus k plus l, so there are only two possibilities. First possibility is what? That it is even. Even. What is even? H plus k plus l, this term. And the second possibility is that it is odd. So this is what here. So there can be two situations: if h plus k plus l is even, and if h plus k plus l is odd. So even means what? Even means h plus k plus l is equal to 2n. Okay, so if we write here 2n pi, okay, so it is like the same thing. So 2n pi means e to the power I. 2n pi means again we can split it into sine and cosine terms, right? If we split into sine and cosine terms, what will happen? We will get a term like sine pi. Of course I will be there, but sine pi means what? Sine 180 degree, which means what is sine 180 degree? Sine 0 is 0, sine 90 is 1, sine pi, sine 180 degree is again 0. So it will be 0, and then we will be left with the cos term, and the cos term will be 1, because cos pi is 1 plus 1. So here you will, so this part here will give you 1 for even, 2n condition, and the opposite will happen for odd. So if this is odd, you will get the negative term. So you can just do it in your like copy line by line, and you will sorry you can do it in your copy line by line, and you will just you can arrive at the uh, conclusion there. Yeah, because it is difficult to do in the laptop screen, for n, uh, for 2n. 2n means even. Yeah. So 2n plus 1 means it is odd. So then if it is becoming as 0, it means that it will be systematically absent, right? So if h plus k plus l is odd, then it will be 0, it will be systematically absent. So this was the question, that what is the condition for systematic absence? So it will be this one. So then we did this. Okay. So what is the deficiency in the raw data collected by the diffractometer? So we have been learning this only for the last 1 hour, I think, that the deficiency in the raw data collected by the diffractometer is that there is no information of phase in the raw data collected. So the phase information is lost with respect to the origin, because the origin cannot be fixed in the reciprocal space. So this is the correct option. So now before going into the last questions, so this is actually, I think, not needed. I put this. You will This will be, I think, more useful in the next week. So when you learn about how we are like dealing with the phase problem. Okay. So we will go to the next question. Which of the following is not part of the single crystal X-ray diffractometer? So, what is the sorry? Which of the following is not part of the single crystal X-ray diffractometer? So, I hope you know what these things are. So, what is the beam stop? What is the detector? And goniometer and all. So these are all parts of the single crystal diffractometer. So if you can see here, when we are mounting the crystal here, so this is actually the beam stop, as you can see. So what it is happening, this is the detector, the CCD detector. This is our crystal. The X-ray is coming from here, and if the when the X-ray is coming here, then the direct beam of the X-ray will directly hit the detector, because the crystal is very small and the X-ray beam has a lot of power in it, and it will directly hit the detector and it can damage the detector over time, because continuously the central portion of the detector will be bombarded with X-rays continuously, because the direct beam has a lot of intensity, so it will go bad very soon. Hence there is something to stop the X-rays, which is this beam stop. So which is made up of such a material which highly absorb is capable of absorbing the X-rays. So that is the beam stop. We have the detector, the goniometer, which rotates. So only this parallel beam slit thing is not a part of the single crystal X-ray diffractometer. Then we have this. What is used to check the proper centering of the crystal? So what is that basically? When we take a crystal under the diffractometer, you want to say something? Yeah, it is there in the later weeks. Yeah, it is there in the later weeks. So you are able to access videos of up to which week? Uh, no, I did not. I did not get your question. You want name of book, or you want the instrument part to understand? What is it which you want? Hmm. Hmm. Okay. Okay, see, the thing is, so the diffractometer, when we are taught the theories, na, so although this is a very advanced course, and really this is a very advanced course, and we are learning at a very advanced level. But when you are talking about the instrumentation, the real life instrumentation, it has gone to a very advanced level. Okay, so right now what is there in the market, the instrument, the diffractometer, you will in the internet you will not get the exact working of that thing, because that is very much advanced. It is twice, thrice advanced compared to what we are reading now. So you want about the instrumentation part. I mean, you want to learn about the instrument, means hands-on training. You kind of thing you want. You are in which week now? Yeah, so uh, ac- yeah, actually in this week 8, so there was this structure solution using Apex and then the Rigaku. Then there was some class where I think he took the data, single crystal data, I think, na? Yeah, actually, I do not. Huh. Sorry, I did not get you. Fundamentals like mane, what is a goniometer, what is the detector, like that. Yeah, which direction actually you want, I am not able to understand clearly. So, can you explain? Means in which direction you want to learn? Yeah, okay. In instrumentation part, like here we get authorized to take the data and all, like what strategies to give and all. So that is most more software part. So you do not want that. Okay, okay, then I have to check and let you know. Yeah. Hmm. So basic instrumentation part, right? Like means how the things work. Means from the some engineering point of view, something. Yes. Okay. Yeah. So. Uh, yeah. So some they in the so this Rigaku, which is who gives this XRD. So there are two companies, Rigaku and Brooker. So we in our institute we have Rigaku. So this Rigaku holds the summer schools for yeah. So like it was I attended in 2020. It was also there in 21 during the month of June, July, like that. Rigaku. So you can see my screen, right? Okay. So if I search, maybe you will get. So you can see this. This is a forum, Rigaku Oxford Diffraction Forum. So here, so you can see this Rigaku School for Practical Crystallography, January 2022. So it was so maybe next year it will have again. So here they hold for both, for single crystal also, for powder diffraction also. And then there are some advanced topics and many things are there. Here about that instrumentation, if there is something or not, I really do not know. search. ये तो सब jobs आ गए. Okay. Brooker, actually I do not have much idea because we do not have any Brooker instrument here. This to all jobs came. I do. Yeah, okay. We also have powder XRD from Liverpool. So about your instrument, I do not know the name of any book or something where an instrument part is no details about the instrument is there. Uh, yeah, that is for sure. Yeah, actually, the operator who is there here, so like we have an operator for NMR, so he is very expert on this NMR from those instrumentation and all point of view which you are saying. So if it would have been NMR, you could have come here and got the training from him. But the problem is here. The operator for XRD doesn't know anything. Yeah. So that is why that person won't be of any help to you. Yeah. But I went to a conference that Aizer Bhopal, I think. Yeah, Aizer Bhopal. I'll let you know in the next live session. That person used to work in industry. So that person is very much expert, and I have heard in that conference that if any problem happens, he is so confident and expert. He opens up the machine and goes into it and then solves everything. Okay, wait, I'll take it once. Yeah, yeah, I'm sharing mine. Okay. Sorry. Yeah. IG89P018 at the rate isergold.ac.in. Okay. So we were, I think, we have one question left. So, yeah. So this rotation angle is used to, center the crystal before taking the data. So when we take the data in the loop like this, where this is the crystal, so we have to rotate it in all degrees, in phi and omega and all that. So that it is properly focused. So to do that, so that angle is called as the rotation angle. Then this also, so this we have covered, I think, that what is the, yeah, electrons, no, this is electron density. So density means number of electrons per unit volume. Volume means it is angstrom cube. So this is electrons divided by angstrom cube, or electrons angstrom to the power minus 3. So because electron density means it has to be number of electrons per unit volume. Okay. Yeah, okay, no, this is electron density, na? So electron density, so rho xyz. So there are some coordinates. So every atom is occupying a small volume in the at which is at the coordinates xyz. It is like occupying some volume. Like it is like dx into dy into dz, or it is written as dv. Some volume element is there because it is electron density in space. Okay, so we will close it here. Okay, so next, I do not exactly work on polymorphism, but I work on crystals. Yeah, so we work on the mechanical properties of crystals.